Hello everyone. So in this video we're going to be talking about three different things. We're going to be talking about, well, two different things. We're going to be talking about electronic loads, DC electronic loads. We're going to be talking, and that includes one that I've made here, as well as the KEL103. It's a machine from Korad. And then we're going to also be talking about battery technology. Okay, so that was just a quick introduction. So one of the things that I want to do is I want to dive more into some of the fundamentals of robotics. There are so many components and there's so much involved in building robotics that it's important to understand a lot of the different elements that go into building these kinds of systems. And in this video we're going to be exploring, in particular, we want to talk about battery technologies. And this is for mobile robots. Now the reason that this came about is because I'm in the middle of a project working on a mobile robotic platform, and this platform has very strict battery requirements, and I'm trying to make sure that I choose the right batteries for this project, and that the batteries are rated correctly. And there's a lot more to that than you might think, and this video I'm going to try and explain as much of that as possible. Now in order to start explaining all of those things, the first thing I want to talk about is electronic loads. And the reason that I want to talk about these is because they're going to help us do our tests. We're going to test out some different, this is a flat pack battery from a tablet, but we're going to test out some different batteries and see how they perform. But how do we test them? Well, there's two different things you need to do to test a battery. The first is you need to charge it, because it needs to have charge in it. And the second thing is you need to discharge it. And you need to be able to discharge it at a variable load. And discharging is essentially what you do when your battery's connected to some load. Like, for example, when you put your batteries in a TV remote, they're always discharging because they have a small load on them. And in this video, we're going to be looking at some bigger loads than a TV remote. But yeah, so what I have here is, this is a DC electronic load. You can build them yourself if you want to, kind of basic functionality. And what it consists of is two big MOSFETs, which are located down here, a couple op amps. Here we have DC input voltage. Here we have our, this is connected to a power supply, and then this is just powering our circuit. Now, that turned off. What's happening here? Well, we're from our signal generator, we're applying a voltage, and we want this voltage to be proportional to the amount of current that we're loading from our battery. In this case it's a power supply, but it will be a battery. And so with this circuit, the way that I've designed this thing is that from here it doubles the voltage that you put in to current. So if you put 500 millivolts in here, you will get 1 amp of load placed on your circuit. Now, although this isn't something that you have to build, if you are interested in electronics, this is a very, very great way to get started. It's a very, very good tool. It teaches you the basics of op amps and the basics of, doing some power electronics stuff as well. So yeah, if you ever are interested, it's good to build one of these. There's lots of different circuits on the internet, tons of different ways to go about building them. Yeah, so I'm just going to demonstrate how this one works first. Sorry about the glare on this multimeter. That's not much better. Maybe that's better. So what we have is this is our current flowing through the circuit. This is, my goodness, this glare. This is our applied voltage to the circuit, and then this is the temperature, maybe backlight. I don't think that helped. And this is our temperature of this big heatsink here. So one of the things is that when we're loading our power supply, that means we have a lot of power coming through it, and that power needs to go somewhere. And in this case, that power is being dissipated as heat. So, without further ado, we'll start by giving this a 500 millivolt voltage, and you can see that we have 1 amp being drawn through the circuit. Now, right now I'm running at 12 volts, but with this circuit you can potentially run from 0 volts up to, I don't know, maybe 100 volts or something like that. It depends on the rating of the MOSFETs. And then you can see, if you look over here, you'll notice our temperature is going up. And that's good, because that means that our current is being dissipated correctly. And this temperature is just a little thermocouple that I've shoved inside of this heatsink. And then you can see that as we turn up the current, or sorry, as we turn up the voltage. So if I go to 2 volts applied, we have 4 amps being drawn, and now you can see that the temperature is increasing very rapidly. Fortunately, I have a fan on here. It's probably going to be loud, but we can use that fan, you know, to help move some of that heat through the heatsink. So this is kind of you know, a basic demonstration of what a DC electronic load is. And if we want, we can connect the same circuit to a battery in order to test out the battery to see, first of all, the battery's capacity, the battery's discharge rate, and then also the battery's discharge rate over cycle life, which is one of the very, very important things that we want to take a look at. But we're not going to be doing that with this basic electronic load. We're going to look at a more professional electronic load that's going to help us do the tests in a much more automated fashion. Okay, so this is the DC electronic load that I was talking about. So this is a professional DC electronic load. So unlike the little circuit that I have, this one is designed to handle much higher levels of power, as well as increased levels of accuracy and also advanced functionality from a software perspective. And we're going to talk about in this video how we've taken the software of this, you know, by connecting it to a PC and controlling it through, you know, Python, how you can extend the functionality of this device even further. And that's something that's very difficult to do with just a little run-of-the-mill device. And this is one that I meant to show earlier, but this is just a tiny little, this is probably the cheapest DC electronic load that you can get. I'm not really sure how much it is, but it has the basic components. You can probably get these off eBay for a couple bucks. It's got the MOSFET, the current sense resistor. If you want to experiment with DC electronic loads, this is a really great place to start. But again, you're just controlling this with a potentiometer or a voltage supply, so it's not very accurate. They're not very good. So this thing, before we actually get to using it, I want to take it apart, take a look inside. I've never seen inside this unit, and see how it works. I have a good understanding, I think, of how this one works. I think it's very similar to the way that our current one, the current demonstration, is working, but with a lot more functionality behind it. So the way this one works is that we have two big posts down here, and this is where you connect your load. And then here you can just set your load digitally. So if you want 1 amp, you set it to 1 amps. Now the nice thing about this is that it'll handle up to 30 amps or 300 watts. And the nice thing about that 300 watt rating is that it really allows us to test high discharge rates on batteries like 18650s. So we can test them at just about, you know, the highest discharge rate that you know, the batteries are capable of doing. Whereas with, you know, that little one that I showed you, I probably wouldn't be you know, doing more than 50 watts on that one, whereas this one will handle you know, 300 watts. So it's much, much different. So again, before we turn this thing on, we're going to take it apart and take a look inside. I finally have a tripod, but it's a bit garbage, so I might have trouble framing up this scene. Okay, and we're in. So this is the inside of the DC electronic load. So the first thing that's going to probably stick out to you is this thing. And this is what we're really interested in, because this is where all of our current is going. Or all of our power is going. So when we're taking, you know, our battery and we're discharging it, all of the energy that's built up inside of here, not built up, but all of the energy that's chemically stored inside of here is being dissipated as heat into this block of aluminum. Now how that's being done is through all of these MOSFETs on the side. You can see these guys nicely arranged all along the side here. And then all of the circuit down here is being used to control those FETs. So there's some probably some analog circuitry at the front end. Here we have a current sense resistor. You can see that there's some input protection, just because this is a high voltage machine. Microprocessor, some just voltage regulation. But it's a very, very nicely laid out machine. It's very clean on the inside. It doesn't seem like there's anything too weird going on. The transformer's nicely isolated. The cabling's very clean and straightforward. We can see we have a nice big mechanical switch over here. So I don't want to get too much into the electronics of this thing, but it's a very nice machine on the inside. Now what we're going to do is we're going to take a look at this thing's functionality. and see how it works, you know, and see if it works as well on the outside as it looks good on the inside. Okay, so before we dive into some real battery testing, we're just going to talk again quickly kind of about this unit now that we've opened it up. You know, at least we can, you know, we can actually use it. So again, this is a KEL103. It's made by Korad. So Korad, they make power supplies, and they also make this DC electronic load now as well. It's a relatively inexpensive unit compared to other electronic loads, but it performs very, very well. This one I've been using for a while now. I use this you know, in my day job for all kinds of stuff, and it's kind of my go-to load. So one of the things that I've done for this is that I've written some Python software driver libraries for driving this thing over Ethernet and USB as well, I guess. And this thing comes with some software, and I think it may have some LabVIEW drivers for it as well, and then it also has just a PC GUI. But in order to do some advanced testing, you know, you want to be able to control it programmatically. And I do like to automate a lot of testing equipment. And generally, the first thing I do whenever I get a new piece of testing equipment in the office is you know, write a Python driver library for it, so that we can actually interface with it. Yeah, so this has been, you know, a great unit, so hopefully I can show you guys kind of some of the things that you know, I do with it. So the first thing we'll do is we'll turn it on. So what you'll notice is that we have a couple displays here. So we have our, if you guys see that line scanning on the camera, don't worry that this isn't doing that. It's just the frame rate of the camera. So you can see that we're at 0 volts and we're at 0 amps. Now the voltage on this is actually quite accurate, at least down to below a millivolt. And I know that sometimes I'll just connect this to things and just use it as a voltmeter, you know, even if I'm not using it as an electronic load, because it turns on quickly and you can connect things to it nicely. So 0 volts is currently on our terminals, so I just have some banana plug shoved in here in a really bad way, but it works. And we have 0 amps, and then we have a 1 amp set point, but it's not turned on. Now there's a bunch of different functions and there's a bunch of different memory things. I'm going to go into one of them a bit later, but right now we're just going to talk about, you know, the basic function of this. So you can see that we have 3 or 4 buttons here that have the C in front of them, and these are very crucial, and this is very good that we have all these options. What these allow us to do is they allow us to operate this in 4 different modes. The first is constant current. So if we want to operate at 1 amp, we want to always draw 1 amp no matter what the voltage is, we use constant current. If we want to always draw it at some particular voltage, and then constant wattage is very good, especially when you're testing, you know, power supplies or batteries, because this allows you to draw at a constant wattage. So for example, let's say that your, you know, motor drive system requires, you know, 25 watts to act continuously. Instead of testing a constant current and seeing, you know, how long until your battery shuts off, it's better to test at constant wattage and always draw 25 watts, because that's more of a dynamic representation of what you know, a motor driver might actually look like. And then also in constant resistance mode, so this machine just acts like a big resistor, so you can set the resistance of this thing. So you'll also notice that the resolution is pretty high, down to 100 microamps. I find that, you know, it does, and we'll see it in the test too, but it loads quite well, especially in the, you know, below, I forget what the ranges are, but below 10 amps, it's very, very accurate. Above that, I think it, you know, the accuracy maybe goes above a milliamp. So I'm just going to connect this battery. This is just one that I've had kicking around. I don't know why it's still kicking around. Probably because I don't like batteries out of sight, because they do bad things. So you can see here that we have some voltage. And you can see that we're not drawing any current. So the first thing is, if we want to just draw 100 milliamps, we just turn it on, and then you can see that right away we're drawing our 100 milliamps and the battery's kind of loaded. Now this thing is already at a lower voltage. We're just going to crank up the current and see you know, when this thing kind of stops taking current, just for fun. No real purpose behind that. So first we'll just draw 1 amp. So you can see the battery voltage drops down significantly, because it's under load and we're drawing 1 amp, but it's taking 1 amp just fine. And this is important because the battery's discharge rate is very, very important to the application, especially in automotive applications and anything that involves drives. For example, a Tesla battery, you know, when a Tesla car says, you know, okay, yeah, my battery's dead, the battery's not dead at all. The battery's got tons and tons of capacity left. but the problem is that it cannot discharge at the rated value anymore. So now we're going to turn it up to 3 amps. Fantastic. Oh, so you can see that it dropped out there. So we kind of overdrew this battery and hit its current limitation. You know, at that voltage, and the battery is just, you know, kaputs now. So it needs to be charged and turn that off and brought back to life. So yeah, so now we're going to dive into some more interesting things. So this is our battery testing setup. Now there's two different things. So I've brought in another piece of equipment. This is just to measure temperature for safety. I would use just a multimeter, but the problem is that their screens turn off and these tests run for a really long time. But what we have here is these are KEL is the brand name. I think these are HG2s. They're a Samsung cell, and they're very, very good cells because they have a high discharge rate and a high capacity, something that's quite often very hard to find together. And what we want to do is we want to see if these things live up to the manufacturer's specifications. So these batteries are rated at having 3,000 milliamp hour capacity and are capable of a 20 amp discharge rate. So we're going to test that. So I've got, this is just a sample one, but I've got 3 here, and then I've got another one in the charger right now. These are all fully charged by the same charger. How we have this set up is we've got a thermocouple taped to the middle of the battery. One of the things that can happen with unprotected cells is that they'll get too hot and they can damage, or you can have something catastrophic fail in the battery. Now the next thing is how we connect to the battery, and this is very important too. Some 18650 holders don't allow high amounts of current. In this case, what we've done is we've taken a standard 18650 holder and soldered on these lugs onto the end of it. And I measured the resistance from the terminal here to the terminal on the device, and it's less than 10 milliohms, so there's not a lot of resistance. These are the cables that come with the KEL103. They're very, very big, very large cables, capable of handling a lot of current, which we're going to see shortly. Yeah, so how we're going to do this is I'm currently connected to this through my PC, and I'm running the Python script that will test batteries, and that is linked in down below in the above the comment section. You'll find the link on GitHub there. So yeah, I'm going to just show you some quick time lapses of this test, and then we're going to talk about the test afterwards. Okay, so now that we've finished the tests, we've gone through and tested all of these batteries, and I'm just seeing if there's any capacity left in one of them. Yeah, the results were kind of as expected. One of the things that happened that was pretty interesting was the battery started to get very, very hot, and above 10 amp hours, above 10 amps discharge rate, I had to cool it down just with an external fan. Otherwise, the batteries were getting way too hot. You couldn't even touch them. So that's something to be aware of, and it's a good thing we tested it, because now we know that if we discharge this continuously at 20 amps, the battery is actually probably going to catch fire, or I don't know. Yeah, but definitely not high discharge rate in industrial environments. Anyway, so now what we're going to do is we're going to go and take a look at the graphs so that we can see what the actual difference is now that we've done that test. What the difference is. Between all the discharge rates and how it performs on this battery. Here you'll see that we have all of our results, and they're all compiled into these 4 different graphs. Now, you'll have to excuse me because some of the headings on the graphs are a little bit off. I didn't realize until afterwards. So the first thing that you're going to see is here we have our 5 amp hour discharge rate. And what you'll see is that we have an excellent curve, and we actually have a capacity of 3.09 amp hours. And that's actually above the manufacturer's rating, and that's excellent. And then the next one over here, you'll see is our 10 amp hour curve. So this one, again, you'll see that when we first start to load it, it drops down below 3.5 volts, where the 5 amp hour test, the 5 amp test stayed above 3.5 for a while. So you'll see that, as the harder the load that we apply, the lower the efficiency of the battery. And the reason for that is because of the series resistance of the battery. Then down here we have our 15 amp curve. This is when the battery was starting to get very, very hot. You'll notice that it's almost below 3 volts, the operating voltage of this battery. And then here finally we have our 20 amp hour test. Our 20 amp test. So we were loading the battery at 20 amps. You can see that as soon as we turned the load on, the battery voltage dropped below 3 volts, and the capacity of the battery is actually only 2.48 amp hours. Now this is to be expected because a lot of that extra capacity was being dissipated as heat in the battery because of the lack of efficiency at operating at these curves. So the manufacturer specified this battery at 3,000 milliamp hours, and I would say that yes, it is definitely a 3,000 milliamp hour battery. But one of the things to be cautious about is if you're ever going to use this battery, is that you are cooling it when you're getting to much higher temperatures, because even in the 10 amp hour test, we saw the battery get to about 70 degrees before I started putting the fan on it, just to kind of prevent any catastrophe. And I'm sure something like that could happen here. One of the downsides to this battery is that it doesn't have protection. So then, if you want to do this test yourself, you can go to my GitHub page and go to, oops, I lost it. Go to the POI Korad, and then if you go into examples, you can see that there's the battery curve example here. And if you want, you can look at the code. It's pretty simple. It's just matplotlib and some other stuff. More information is in the wiki, and then if you want to run the examples, this is a brief explainer of what the example does. So yeah, anyway, thanks, and happy battery testing.